This is the first video on population genetics. So in this unit, we're going to be looking at inheritance in a broader context, in the context of an entire population. We focused previously on thinking about what alleles that you inherited from your parents and what the probability of inheriting those alleles was. In this unit, we'll be looking at allele and genotype frequencies in the entire population, and we'll consider your chance of inheriting a particular allele as a chance that is associated with your population that you live in. So the first thing we'll look at is two important quantifications. We can quantify the frequency of different genotypes in a population, and we can also quantify the frequency of particular alleles in the population. So this example is an example of frogs that live in a pond. And there's two alleles in this population for the A gene. There's big A and there's little a. And each individual either has two of one, or it could be also heterozygous. We can quantify the genotype frequencies by just counting up what the genotypes of individuals are. And so if we count up the number of individuals with big A, what you'll find is that there's 5 individuals with that genotype. And we can determine the frequency of big A in the population, which we'll designate as F of big A, by simply taking the number of individuals, which would be 5, divided by the total number of individuals, which would be 16 in this case. We could do the same type of calculation for the frequency of heterozygotes and also for the frequency of individuals which are little a. Allele frequencies are different from genotype frequencies, and so this is not paying attention to which ones are together in one individual. It is simply counting up the total number of big A alleles or the total number of little a alleles. And so, for example, if we think about what the frequency of big A would be in this population, we would count up the number of big A alleles, and so we could go through and count all those. So these top individuals, this one has 2, there's 3, 4, there's 5, etc. And these are already counted up for you. There's actually 18 big A alleles in that entire population. And in order to determine the frequency of big A allele, we would divide that by the total number of alleles, which is 32 in this case. The same thing can be done to calculate the frequency of little a, and we're going to name the allele frequencies P and Q. And so P is generally the frequency of the more abundant allele in the population, whereas Q is the frequency of the less abundant allele in that population. One other thing I'd like to point out is that the genotype frequencies will all add up to 1. And so there are only 3 different types of genotypes that could be present in that population. And if you calculate all of these, each of these should be a fractional number. You can check your work and make sure you calculated them correctly by simply adding them all up. The sum of all of the genotype frequencies should be 1. Likewise, for the allele frequencies, P plus Q, or the frequency of big A, plus the frequency of little a, should add up to 1 as well. In some cases, you may find a bit more complex information. So in this example, you are given the number of individuals who have a particular genotype. So this example is looking at the MN blood antigen. There are 2 alleles of this gene, LM and LN, and there are 3 different genotypes that are present. In this case, you're going to use a formula to count up the total number of each allele and divide it by the total number of alleles in that population. And so, for example, if you were calculating P, which in this case we would say is the frequency of the LM allele, You would look at the individuals who are homozygous for the LM allele. Each of those individuals have two LM alleles, and so you would count them up by multiplying that 1787 number of individuals who are homozygous times 2. Then you would add the number of individuals who are heterozygous, and so each of these individuals have only one LM allele. Finally, you would divide that total by the number of individuals times 2. And the reason why it is the number of individuals times 2 is because each individual has two alleles of this gene. You would go ahead and do the same for the second allele, for the LN allele, and usually it's a good idea to check your work and make sure that P plus Q equals 1. Just one point is that for alleles on the X chromosome, things are going to be slightly different. And you'll have to take into account the sex of the individual, since males would only have one X chromosome and females would have two X chromosomes. Next, I'd like to introduce the Hardy-Weinberg principle. So this principle was independently predicted by two different individuals, one of them named Hardy, the other named Weinberg, and this was introduced in 1908. So their principle is that assuming a population meets certain criteria, the allele frequency in that population is not going to change over time, and also the allele frequencies that are present in that population will predict the genotype frequencies that will be observed. Now, the conditions that that population needs to meet are listed here. So the population needs to be randomly mating, it needs to be relatively large in size, and it needs to be not affected by mutation, by migration, or natural selection. I'll go more into those examples of times when populations are not in Hardy-Weinberg equilibrium in the next video. So what I like about the Hardy-Weinberg principle is that it is so very straightforward and logical, and it is very easily understood based on the probability work that we did earlier in the semester. So I'd like to first think about this situation of normal inheritance, and this first one is not a Hardy-Weinberg situation. So in normal inheritance, we've done these Punnett squares in the past. So if two parents are both heterozygous for the A gene, we would make a Punnett square that looks like this, where the top indicates the gametes that come from one parent and the side indicates the gametes from the other parent. In this case, the chance of getting a big A or a little a from the parent on the top is equal, and so we draw these boxes equal in size. Also, the chance of getting a big A or a little a from the other parent is equal. It's a 50-50 chance. Now, Punnett squares make this nice grid in which all of these possibilities are equally likely, but I'd just like to point out that we can use probability to actually figure these things out. So for example here, what is the chance of being big A, big A? So we know that's 1/4 based on the 4 possibilities here in the Punnett square, but we can also figure this out by probability because from the one parent on the top, we have a half chance of getting a big A, and from the other parent, we have also a half chance of getting a big A. And so to figure out the probability of getting two big A's, we would simply multiply 1/2 times 1/2, and that would give us 1/4. Same situation applies for little a, and for heterozygotes, there are actually two ways that you could be a heterozygote. One of them is that you got big A from the parent on the side here. The other way is that you got big A from the parent on the top. And so the chance of each of them is 1/4, and you would simply add those together or multiply them by 2 to indicate that there are two different ways of getting big A, little a. And so the probability would be 1/4 plus 1/4 or 1/2. Now, when we think about population genetics, we change our approach. And rather than thinking about what your parents have, we think about what the chance is in the population in which you live for getting either big A or little a. And so I'm going to talk about a particular example in which the frequency of little a in the population is 0.2 and the frequency of big A is 0.8. So it would be 20% of the alleles are little a and 80% are big A. So in this case, we do the same kind of thing and we think about what's the probability of getting big A, big A. If the allele frequency of big A is 0.8, then chance of big A from one parent is 0.8, chance of big A from the other parent is also 0.8, and we would multiply those probabilities together since they both have to be true. The same type of thing can be done for little a, little a. If the frequency of little a is 0.2 in a particular population, then the chance of getting two of them is 0.2 times 0.2. Last one is the heterozygote, and there are two different ways to be a heterozygote. For this one box, we would say the chance of big A is 0.8, the chance of little a is 0.2, and we would multiply those together. But there are two ways to be heterozygous, and so we can calculate the probability of that by simply multiplying 2 times 0.8 times 0.2. Now I'd like to discuss the way in which we're going to use a general formula or making a rule about how we can calculate these genotype probabilities. So if we call the frequency of little a Q, and if we call the frequency of big A P, then we would make a Punnett square like this, where the chance of getting big A is P and the chance of getting little a is Q. Chance of getting big A would be P times P, or P squared, and chance of getting little a would be Q times Q, or Q squared. There are two ways to be heterozygous. That would be P times Q, and since there are two ways, we multiply that by 2. So this down here on the right is the Hardy-Weinberg principle. It says that if you know P and Q, it will predict the genotype frequencies that you will observe. One other thing I'll mention is that I drew the Punnett square in these examples asymmetrically because in this case, and very frequently in the general case, the frequency of the two alleles in the population is different from each other, and specifically, big A is more abundant than little a. So the Hardy-Weinberg principle is summarized here, where P and Q equal the frequencies of the two alleles. The genotype frequencies can be calculated based on P and Q. One other point I would like to remind you of is that P and Q should equal 1 if there are only two alleles present in the population. And also, if you define the genotypes based on P and Q, so P squared, 2PQ, and Q squared, then all of the individuals in that population will fall into one of those three groups, and P squared plus 2PQ plus Q squared should equal to 1 as well. The frequency of all of the genotypes will add up to 1.